page, those of us who have the laptop here, there is one resource which I didn't really bring up, but every day there is a reading as well. So like yesterday there was this paper. So I know the slides have been difficult to download. This is a big set, but this is a short PDF paper. So if you just want to take a quick read of the material, so same way for today, there is a book chapter. So this book chapter on navigation system, if you click on PDF, it's a short file and that gives you a very quick big picture. Okay. And even for tomorrow, as you see the reading is already here. This is the survey paper. So if you click on PDF, again you will get the big picture. Okay, what is there? All right. Second part is, yesterday, thanks for taking time to fill out the intermediate course review. So I went through those, and overall seems like things are going well, but there were a couple of things that came in suggestion. So number of feedback forms mention interest in having a hands-on lab. Okay. So this is something I have passed on to Professor Mins. But in order to do that, as you can imagine, we need to make sure that people have access to computer, right? Either people bring their own or we are in a lab with computers. And second, we need to have a common set of software, right? So the way before, this course was set up, we didn't have that. So we may not be able to do that during this course. But I want to point out a couple of things. So there are a number of labs on my own course website, which I will point to. So if you have access to Oracle Spatial, for example, then everything we did yesterday, there are a bunch of labs. You can just look at the problems, don't look at the solution, and you can try it out. But the solutions are also posted, so I'll show that. In those labs also, there are a few exercises based on web-based resources like Google Maps, Google Earth Engine. So I'll show that, and I said if you have interest, you can try a little bit. But Professor Mins was saying that you may have opportunities to have a follow-on engagement. So courses on campus here at JNU may add a similar lab. And same way, I think, not only in computer science, but in geography also, they sometimes offer the hands-on part. Okay. So I'll quickly show where these labs are in case you're interested. So easiest way to navigate, to find it is to start from my home page, which, again, the URL I had listed here. If you drop the Gian part, then the first part is sort of this URL. And in this, there is a teaching section. So and as you can see, this was the course we are teaching this semester. If you go to the course website, and there are many tabs here. The one where lab is a homework tab. And then here you see 4 labs. So the labs which will overlap with yesterday, for example, you will include lab 2, just to give you a flavor of what's there. So this is based on Oracle. One can also do similar thing on PostGIS as well, but at least the Oracle part is all tested. And it gives you some data sets. Remember the country, city, rivers. The toy example, we had only half a dozen rows, but this probably would have many more. So countries may have 180 or so entries and so on with actual geometries and polygons. So you can download those and and load it and so on. And this gives some examples, okay, how you insert it and so on. But then later on, it also asks you to write queries. So here is a distance-based query where the solution is given, but then it also says, okay, try now writing queries like for these, right? And you can try it on your own. And if you wanted to see a solution, going back here also you can click on the solution part, okay, and just verify. Now some of these labs will also go beyond and do other things. Let me see. So if you scroll down, besides Oracle Spatial, you will see this still spatial queries. It has other kinds of activities as well. So this one is saying, use your smartphone to record your trajectory, right? So it's a different kind of activity. Or if you look at another part, this is somewhat relevant for today. And there are websites which allow you to do geocoding and reverse geocoding. So given a place name, it will give you lat long, or given a lat long, it will try to get the closest place name and so on. So there are a variety of these are available. But as I said, within this setup, actually we didn't really anticipate, and we are not sort of in an atmosphere where we can do anything within the days, but follow on hopefully, and we'll hear more from. Do you want to add something at this point? Or essentially, if the student feedback and what are the possible ways for them to, so yeah, you can use the mic.
Thank you for your feedback, and Prasa has gone through them, and thank you for giving in. And then some of you were surprised why we were doing it intermediate, but the purpose is to also see if it is possible to meet certain expectations that you had from the course. And to the extent it is possible, Professor has mentioned, especially regarding the lab. But the second thing is we could, outside the framework and scheme of Gian, the school, Dr. Aisha, and maybe some more of us, and Prasad also has one of his very fine students in the city in IIIT Delhi. So we could coordinate, as well as cashing on the expertise of this university in this very department, this very lab, Carto Lab, as well as we have certain projects which this center has, and our environmental sciences. They do have very fine labs equipped with softwares, which are only very GIS softwares as well as otherwise. So probably our school has Oracle and Oracle Spatial, I guess. Even if they don't have, so it's like a complementary scenario. So we could design another short or semi-short course, which can come next semester sometime. After we've done threadbare work on designing, because Professor had everything in one place, and it's years of his experience. But we would have to bring the puzzle pieces together. So at least it may take a semester for us to do that, and maybe it can have other flavors also to add, and probably if your feedback and in the end of the course in terms of or you feel you're free to please email to Dr. Aisha or me as to what can be the next stages, also your expectations, so that we can actually tailor make it as a follow-up or the second stage to this course. So I think that way I would like to present that, and to those who are from the university and who are in the neighborhood of this university, for your information, this particular center as well as the environmental sciences, they have a master's level course on GIS and remote sensing. Whereas I used to offer a geospatial informatics from a very computer science and data analytics perspective. I've designed that course complementing their course content. So these are some of the information which prevail in the university, and we look forward to taking the next step after this course.
Yeah, great. Great. And there was one other feedback which probably we can try to address, and that essentially said that instead of waiting till the end at the tutorial for all the exercises, maybe this long lecture, 2 hours of lecture, we should have a few short exercises, more exercises within the lecture. And that is, again, a great idea, and we'll try to do that, today as well as tomorrow. Okay? Great. And then the last part, where we actually asked for some input, we didn't get a lot, but I quickly wanted to have a show of hands. So day 5, right now the agenda is somewhat open. And there are 2 sort of, again, lecture hours, and I had asked, put up few topics here, and I was trying to assess the interest. So let's at least do a show of hand. How many of us would be interested in a discussion of evacuation route planning? So about 10 or so. Okay. How many will be interested in spatial big data? Okay, so a few more than 10. Okay, so clearly these have a lot of hand. Okay, I can explain what this topic is. For computer science, it's a new topic, but if you know what this topic is, nexus of food, energy, water, how many of us would be interested in that? Okay, about half a dozen. All right, okay, good. So that pretty much tells us at least the interest. So we'll probably pick the first two, the evacuation and spatial big data for the discussion here. Any other feedback, any comments, questions on material we covered last 2 days before we start new things? Yeah, please go.
I just want to know, in this course, there are any algorithmic approach to any problem, tailor-made query, any algorithm, especially for special data mining?
Okay, good question. So the computer science, a lot of times when we have discussion, some of the core ideas are algorithms, data structures. We like to scale up and so on. And as you have noticed, at least yesterday there were no algorithms. We were at a declarative level. Day one there were no algorithms. So I heard a number of computer scientists are saying where is the core of computer science, right? So today we would get into some algorithms. Okay, some of these will be familiar, basic graph algorithm, but there will be hopefully at least one new algorithm, hierarchical routing, that would be new. So hopefully, for computer science, that will give us a little bit more of the algorithmic flavor. But people who are from outside computer science, so there is again an interdisciplinary kind of discussion. They don't always enjoy the algorithmic part, right? So in database world, the way we think about things is a little bit different than the traditional computer science. Okay, so in data world, we view discussions at 3 levels: conceptual, logical, and physical. Okay. So physical data model is where algorithms, data structures reside. Okay, and certainly those are important for scalability. But if you want to reach interdisciplinary audience, you don't want to start there. Okay, it's easiest to have communication at the conceptual data model level, and which is what sort of happened a little bit yesterday, but a lot more at the logical level. Okay. So. And again, yesterday, if you remember, we did have a show of hand across disciplines and sectors and so on. It's a pretty multidisciplinary audience. So bulk of the discussion will stay at conceptual and logical level. And today in the discussion, actually, you will see those 3 levels mentioned very explicitly. And today we would spend fair amount of time on physical level. Not only algorithms, we'll also show you some data structures to store graphs. Okay. So people who are from outside computer science, bear with us during that physical data model discussion. But these are sort of the, when you talk to 2 disciplines, each discipline values different things. And as we build the bridges, we both have to get used to the interests and values of both sides, right? So there would be areas where each discipline would feel that it's not my, cup of tea. It's maybe too high level. Conceptual may feel not so rigorous to computer scientists. But at the same time, when we go to physical level data structures and algorithm, they may feel too much detail for people outside computer science, right? So it's an interesting balancing act in this course to bring the 2. But today you will see all 3 layers very explicitly. Okay, but tomorrow we probably won't have as much algorithm. We'll probably stay at logical level because there will be enough just at mathematically rigorous discussion, but at logical level. Okay. Spatial big data discussion, again, I would probably not get into major algorithms, but there would be some discussion of platforms. Okay, what are the platforms and so on. Okay. Yeah. Yes, go ahead.
So my suggestion is
Right.
a course like this.
Right.
Once it is declared and it is on net,
Right.
then people who register give some kind of, in the confirmation, get
Right.
some links to pre-read before we come for the course.
Yes, yeah.
That
Yeah.
keep us better posed for understanding when we come.
There, yeah. And this is also an excellent suggestion. So again, we'll pass it on to Professor Mins and so on. But remember, there will be another course evaluation at the end of the course. So it's also good to put those suggestions. Because these readings and slides and so on, again, at least for the coming days, you have some of those up there.
Yes.
So and if you feel that helps, then it's good to enforce that. Good. All right. Any questions, any issues that we have from last 2 days that we want to discuss before we proceed? Okay, good. All right, so let's maybe then get started. Okay. So today, we are going into location-based services. That's from user perspective, but from computational perspective, we are calling them spatial networks or spatial graphs. Okay. So I will very quickly go through the motivation, and then we'll get into the computational part. Okay. So outline for today is to first go through the motivation use cases. And then, as I mentioned, we'll start with this conceptual model. In this case, it will be the mathematics of graph theory. Then we'll go to logical model. So go back to the SQL and say that, at least at SQL level, what kind of graph computations are supported. And these are two new SQL statements we'll look at. And then finally coming to the areas which computer scientists have been looking for, looking at some data structures and algorithms related to graphs. Some of them, again, would be very basic algorithm. Many of you will know, but at least I will make sure there is one new algorithm. So hopefully for computer science, there will be some new things. Okay. All right. Okay. So here, again, the goal is to start with the motivation and talk about why spatial networks are important societally, why we should all learn about it. And you will very soon see why I'm emphasizing it. So first use case is navigation. Okay, so all of us use Google Maps, so we have actually seen use of road maps, and it's a very classical case. Okay, so if we have an extra battery, we'll be good. So navigation, as we know, is a pretty age-old human activity. It started with trading as well as exploration. And it continues to be a fairly interesting thing today, and Google Maps is an example of that, right? So, these devices I don't have to show anymore. Probably most of you have used them. We can now use these navigation apps on smartphones. Before that, they used to be on the web with MapQuest and so on. And you have many, many different services around that. So you can also ask, where am I, what's around me, where is the nearest hospital, how do I get there, and things of that kind. Right? So all of these are examples which are location-based services in navigation. Okay. Let's go to other use cases. So I said in terms of a broad family, you have notions like location-based services. So most of us only look for where we are, but there are two associated services which people in GIS terms they talk about it. One is called geocoding and other is called reverse geocoding. And what they are referring to is the following. When we want to answer the question where am I, this can be answered using very different kind of representations. One representation is in numeric, like latitude and longitude, right? Assuming very simple spherical coordinate system. But those numbers are very useful for computers. They can use it for graphics, they can use it for computation. But for most of us, they don't mean much, right? If I gave you lat long of a place, for most of us, it doesn't mean much, right? But so most of us, we use symbolic names, right? You want to say I am in Jawaharlal Nehru University, and that's a place name, or in social science building in Jawaharlal Nehru University. So given this duality, there are services which translate between these two systems. So given a symbolic name, geocoding will give you the numerical representation lat long. And same way, reverse geocoding goes the other way. Given a lat long, it can give you the place name. Okay. And again, I said there are websites and other labs where you can try that one out. So anyone knows the lat long for Delhi or JNU? Yes, two. That's the latitude and 76 is the longitude. Okay, good. But as I said, otherwise you can, there are very widely available websites where you can do that. Okay. All right. Once we know where we are, we can ask the query, what is around me? So show me all the, let's say, petrol station within 2 miles. Things of that kind you can do. And you have probably done that on Google Maps. And then finally, you can ask if I pick one of those hospitals or petrol stations, how do I get there, right? So all of this we have done, so we don't need to repeat it. Let me show you something a little bit different. So spatial networks do not just represent transportation networks. Of course, most of us are familiar with that. If we live in a city, there are lots of other networks, and they are actually thought of as critical infrastructure for any civilization. And I'm giving you a list from the Department of Homeland Security of which infrastructures are considered critical. And there are many different uses for it. People try to protect them in a certain way, or in case of a war, they try to destroy those for the adversary. And you will see many of these. So let's first make sure the transportation is included. Right here. So transportation certainly is a critical infrastructure. In fact, some of you know that Department of Defense in most countries was responsible for making many highways so that they can move troops quickly from one place to the other. Okay? And in fact, even today, some of those highways are considered strategic. So in case of emergency and war, the army would take over those and they would protect it because they need to move things around. So this is very, very critical. But in addition to that, food and many other things, they move through that, right? If the roads or things shut down, that brings down our civilization. But there are many other things. Close to computer science, internet as well as telephone networks, they are also considered critical infrastructure. Okay? But for our discussion, what it essentially means is that if I want a representation of those physical networks, it will look very similar. It will be a spatial graph. So everything we are talking about, even though the examples will come from transportation, they apply to those networks. Okay? Just that they are so sensitive that it's not easy to get that data, particularly telephone networks. And you will see, many others. If you see about water, right? All the rivers and how water move, again, it's a spatial graph, and so on. You can basically see a lot of this. So things we are talking about, even though examples will come from transportation, they apply to many aspects of our civilization. All right. So again, we are trying to now differentiate between what we are going to do today and what we did yesterday. So let's just think about, out of these 4 choices, which is something we are not really going to be discussing today. Probably we discussed it before or and so on. So how many vote for this? Navigation, okay, geocoding, reverse geocoding, or convex hull? Okay, great. So the geometry we are leaving behind. That was yesterday. Okay, now we are moving to the graph world. Okay. And you may want to wonder why. So this is where I will first say that OGIS simple feature type, we had pretty nice geometry, at least 0, 1, and 2 dimension, but it's not going to help us with networks, right? So it did geometry, but you couldn't do shortest path, right? That there was no such notion. And that's where we are going today. And turns out, actually, there is a similar limitation with SQL. So if you looked at original relational algebra, it had some very simple operations called, join. We saw that equi-join, project, and select. And those of you who took the relational algebra and relational database courses, you also know that there is a fundamental limitation of relational algebra, right, which tells you that it cannot represent transitive closure or shortest path. Okay? So if you were in pure relational databases, you could not carry out these kind of computations. So even from database perspective, what we are going to do is new. But in SQL3, this little bit of extension did happen. It went beyond relational algebra to add these recursive computations. Okay, good. So last use case I will mention actually comes from straight away from the GIS domain. So ESRI ArcInfo actually has a package for network analysis, and its name is essentially Network Analyst, and it gives you 2 or 3 different things. Okay, the first is familiar to us. Like in Google Maps, given a start point, a destination, you can get a path, right? So they also support that, but their path, is, Google is also starting to do that, but their path can also have a set of stops, okay, a large number of stops. Okay, in addition to that, they do other things which at least I have not seen in Google Maps, but it's very useful for logistics and for many other planning. Okay, so one operation is called allocation. So if you, let's say, are given a set of post offices, right, and a set of postal customers, then you want to divide up postal customers by the post office. Maybe nearest post office is one way to divide it, okay? And that's called allocation. And this is a very common problem. If you have a set of hospitals in New Delhi, and you again want to divide up the houses in New Delhi by the nearest hospital, that will be an allocation. And this is a common analysis that is done for many, many different types of facilities, retail stores, gas stations, and so on. One more time? Yes. Yes, yeah, and yes, yeah, and this is what I was saying. This is actually ESRI Network Analyst. So I'm listing the functionality of that, the one I had sent you in email. Okay, right. So these are very common operations. Operations research kind of community has been using it for a long time. Right? So I'm just showing you the use cases of graph. That's all. So this is sort of a typical one, and then you can make a service area and so on. Right? Now there is also a reverse problem of that, which is saying, suppose I have a set of hospitals and I allocated people to that, but nowadays you actually do a very simple analysis called accessibility. Okay, how long it will take for any house to go to the hospital, and for certain kind of situation you want to put a limit on the type, right? If somebody has a heart attack, there is a certain amount of time by which you want to reach the hospital, and suppose that there are houses where you're exceeding the time. In that case, you may decide to add a new hospital. Okay, you add a new hospital in order to make sure that those houses, the service time goes down. And that kind of a problem is the reverse problem. It's often called site selection or location kind of problem. So given a set of customers, you might want to decide where to place these new facilities. Okay, again, these are all supported in software, not in Google Maps, but if you went to logistics software, if you went to ESRI Network Analyst, people do that. And commercially, a lot of this has had a very major application in many ways. So site selection is an age-old problem. You can think about, where do you put a steel factory? So first steel factory in India, went to my hometown, which is Jamshedpur, and you can ask why it went there, because there was no population there, at least back then, 1900. But the reason was it was close to iron mine, it was close to coal mine, right? They could put a train line, it was close to that, there was water. So site selection is done for factories. Same thing is done for commercial things. In fact, McDonald's really was a master of this site selection. So they went and analyzed the number of household and income. And for every McDonald's site they pick, they make sure that within a certain driving range, there are enough number of customers with enough income to give you certain amount of business. Okay, and it's the same kind of a decision making. So many companies do that. Obviously, the next one which came along, like Burger King or Subway, they didn't have to do the analysis. They just found out wherever McDonald's was, they just cited next to it. So they do things like that. Yeah. Okay, but this is a very classical analysis. Many companies do that. Okay, many government people do that. You can even think from government perspective and say, well, there are all these rural areas and I want to serve them. Where should I put rural clinics? Things of that kind. And this problem is getting now more interesting because you can have mobile service centers. So where do you put those vehicles? Okay. So this one, again, it's repeating the same point. The graph data type is not supported in OGIS. So this kind of use case, you have to go beyond OGIS and do something different. Okay, that's all it's saying. Okay. All right, good. So motivation-wise, hopefully we are all on board. This is an important topic, and one reason I repeat it, for computer scientists, it's no new news. Okay, graphs are very, very core in computer science, and that's the bread and butter of computer science. They are all there. But if you go to geography department, over last few decades, the transportation geography is a topic that's getting more and more neglected, and which is a sad thing, because that's the fastest growing segment of GIS. But most departments have focused more on the OGIS things, environmental part. Okay, but I guess in this room we all agree this is an important topic. So next, let's look at a few networks. I just want to give you 3 quick examples, and for most of the discussion we will use these 3 networks. Okay, and they will all come from transportation because that's what I assume most of us are very familiar with. Okay. So first one, Google Maps. This is the road map, and you also know the use cases. So given a source and destination, I can ask for a shortest path by distance or travel time or some other thing. You can also, as I said, ask the distance could be, driving distance and so on. So there are different use cases, and most of us have seen these. So first 3 was around shortest path, which is studied quite a bit in computer science. Fourth one was this allocation problem we just mentioned. Okay, operations research studies it a lot, and some computer scientists also study it. Let's look at a second network, and this is sort of a railroad. In this case, we are looking at a metro-like network in San Francisco area, which has 4 lines. So these dots are the stops, and these are different lines. And here the queries may be a little bit different. Okay? So in metro, if you might have seen an app which can ask for things like given a particular line, they are often colored. So given this line, I can ask how many stops are there, or I can ask if I start from a particular stop, which other stops can I quickly reach by changing a train or not changing a train. Okay, you can ask a source destination, I want to go from here to there. Okay, which route am I going to take, right? Things like that. And things of that kind. But again, mostly graph queries, but slightly different flavor. The topology may be different, and this is the second example. Okay. The third example we'll use are rivers. And river network, people may have different analysis. So here we are asking, tell me all the other smaller rivers which contribute water to Mississippi, or you can ask, direct tributaries. You can ask about the reverse question, saying if I have a spill in a particular place, what are the downstream places which can get affected, and so on, right? And this is showing you kind of the river. This is Mississippi sort of going down this way, but you see other like Missouri and Ohio and other rivers contributing. Okay. So many different transportation kind of examples we saw, and we will use these. Okay. All right, so this is again asking, what are the types of questions we can ask? Some of them are familiar to you, like shortest path, the driving distance, but you can ask other questions as well. You can just go and ask about the properties of the network and so on, and the query language will study would have. So here basically I'm expecting you to say all of them. Okay. Great. So with this now, let's start to formalize it. And if you actually ask a computer scientist, how am I going to represent these kind of phenomena? Their first answer would be graphs or graph theory. Okay, and that's the conceptual model we will use. But you will have some small surprises coming there, so I will flag those. But let's at least start from where we all meet. Okay, so graphs are used to represent these networks, and then there are some nuances that will come up. Okay, so in conceptual model, we'll start with a richer version. From database perspective, we actually think in terms of entity relationship model, which can give you a little bit more information. For us, graph is a little bit more lower level, it's going towards the implementation. So let me first show you the ER model of roadmaps. Okay? And once we have this information model, we can go to this mathematical model. Okay? So, all right. And then we'll go to logical data model, which has to do with programming. So we will have abstract data types, and we will kind of use that library to extend SQL so that we can write queries at a logical level. And then finally, that's where traditionally computer science resides. Vast majority of computer scientists love to talk about how can I scale up to very, very large problems, and for that data structures and algorithms are important. And today we would have some amount of discussion, and hopefully there would be some new material for computer scientists as well. All right, so let's start with this. So suppose I'm looking at a very simple roadmap like this, and let's try to see what are the concepts people often use in transportation and day-to-day language before we narrow down to graph. Okay? So this has concepts like first the notion of roads and streets, and we all know that. For example, this 4th Street Southeast would be an example of a road, right? Road intersections will be another part. So here 4th Street and 6th Avenue, they intersect. That's a road intersection, right? We can talk about road segments. So this is the long road, but the piece that connects adjacent intersection, that is a segment. Okay. So now you can start to think about edges coming up, right? Nodes and edges kind of coming up. Okay. We can also talk about turns. And all of us who drive or walk, we know what it means to have left turn and right turn. And at this point, people who are into graph theory may start to think about how you represent turns in a graph. Okay. So things starts to get a little more complicated. Okay? And you have seen these kind of restrictions and so on. All right. So for ER diagram, I said, basic core entity is a roadmap, and we are going to now break it down into sub-entities. So the first simplest model, and that's the universal model of roadmaps. Every roadmap that you will find commercially would essentially model these roadmaps as a collection of road intersections, and they will typically be the nodes in your graph. And road segments, they connect the adjacent road intersections, and these will be edges. Okay, so this is your classical or the most accepted graph model for road maps. Okay, all right, but we know there are other notions here, and as I was mentioning, some of them, if you use just this much in your graph, then it will be a little more tricky to represent other things like turns. Okay, and I will show you a little bit of teaser of what it does. Okay? So there are other notions like left turn, right turn. You even have notions like route and street. So those are like path in your graph, right? Okay. So, but all of this in some sense, you can generalize them and think of them as a sequence of segments. Okay. Turns usually is a pair of segments, sometimes sequence of 3 if you talk about a U-turn. D certainly is a long collection of segments. Okay. All right. Then there are other things that come with the roadmap. Usually we have a street address. Okay. So you might say something like 200 Union Street Southeast. Okay. And most roadmaps, they support that in a native format. And in fact, they do both geocoding and reverse geocoding. And the way they typically do that is very simple. For every road segment, and on each side, they would have the highest and lowest street address. That's typically what they store. And the street address, if you are looking for, if it is not one of those, then they will do linear interpolation. And that process itself can introduce some amount of positioning error. Okay, but that's typically what they do. But most road maps, they will come with street address range. They will also come with a database of point of interest. All right, and then this is where you can have symbolic or numeric, so geocoding, reverse geocoding down, this goes here. One small vocabulary issue for computer science folks, okay, gadgeteer, how many of us know what that is, gadgeteer? Okay, someone from geography, could we help us with what is gadgeteer? Okay. So it's essentially a master list of place names or master list of road names, okay? And geographers have spent a lot of time making that list, and it's now widely used. So if you were in Google Maps and so on, and when you simply say Jawaharlal Nehru University, it usually goes to the gadgeteer to say, okay, do I have this name registered? And if I have the name registered, where is it? Okay, so there is a database which gives you well-known place names and its locations. In England, in US and so on, this has been a tradition. They have a pretty rich gadgeteer. In India, not as rich a tradition. So you would know the major places like the universities and government buildings. But once you go to rural India, these things are very sparse. In fact, some of you might have heard the news, at least UP, they asked, because they have a very large police force, and they actually recruited and they gave a quota. So many police persons, they went and they digitized, hundreds of places individually. So they made a very large gadgeteer of rural UP areas. And those are very interesting resources. If you have to work in rural areas, knowing that such databases exist can make a difference. Okay. All right, and then finally you have coordinate system. So this was one question that had come up. So, if you are going to do geocoding, go from street addresses to lat long, then you need to also know which reference system is being used. Okay, that's all. Okay, so now we are going to switch to graph, but one thing, I would very quickly contrast is the following. When we are in entity relationship model, we can have many, many relationships, right? So in this diagram, how many relationships can we see? Okay, so each of these line is a relationship. You see many relationships, right? How many relationships can we model in a graph? Okay, people who, in computer science, graph, entity relationship diagrams. What's the connection? How many relationships are modeled by a graph? Okay, any guess? 1, 5, 10, how many?
Can you know about the number of nodes?
Yeah. But edges represent how many different types of relationship from this perspective? Only one relationship. Okay, one graph gives you one relationship in this picture. So this is the first thing to realize. So the classical roadmap, the only thing it is doing, so you pick your node. You can pick any of this as your node if you want. So classical graph model, these are the nodes. Okay, these are the edges. And what is the relationship among nodes they are representing? Connectivity. That's it. If I want to talk about turns, it's a different graph. And in that graph, your nodes are going to be the segments, and turns are going to be relationships. So it's a different graph. So this is one thing to remember, because in computer science, we seldom discuss where do graphs come from. Okay, we are always given a graph and we are ready to write algorithms. But if you are trying to model roadmaps, graph is not a really rich representation. You have to take your pick. If you are willing to focus on one relationship, then you got a graph and you can run with your algorithm. And everybody does this. So when you do that, you now have to wonder, how do I restrict left turn and so on? And I will show you example what happens. There are different ways to do it, but it's a pretty non-trivial problem. Okay, let's continue on. Let's go to the comfort zone of computer science. So we chose one relationship, and let's just stay with connectivity for now. So once you do that in a mathematical abstraction, a graph is a pair. You have a set of nodes and you have a set of edges. But this set of edges is representing just one relationship in a ER diagram. Okay. I see. So you have a set of nodes and then you have a set of edges. All right, let me just give it a second. Okay, let me just restart. Maybe it froze it. Sorry about it. Back in this is okay, good. All right, so in a graph model, mathematically it's a pair. We have a set of nodes and we have a set of edges. And usually in computer science, we don't think about the meaning of nodes and edges, but in this case, we are focusing on roadmaps. So if you have this particular roadmap, the default model that everybody uses is where the road intersections, okay, these are nodes, and then these road segments are the edges, right? So you can actually overlay these on top of each other and you can see the correspondence, okay? But that's basically what is going on. So we will work with this kind of a graph for a while. But as I told you that, each graph models only one relationship, okay? However, given that road maps are spatial in nature, there are many relationships, right? Turn is one we already know, but you can even invoke other relationships from OGIS, okay? So there is a lot more information that is in the road map than it's in your graph, and you have to remember that, okay? This is another mindset change, which I will try to emphasize. Mathematics and computer science, they are artificial domains, okay? In those domains, we can create anything and be correct and complete, okay? But when you come to physical world, like in geography, okay, or environmental sciences, the models that we create are never exact. They are an approximation of your reality, okay? This is never emphasized in computer scientists, so this is just for computer scientists to remember, okay? And the progress is made by improving the approximation, okay? This is not natural for computer scientists to think about, but for physicists, for biologists, that's always very obvious. And that's what is happening here. This is an approximate model of this roadmap. And as we go along, I will again and again come back to this and say, oh, can I make this approximation better, okay? So don't, as once I showed you the graph, don't forget there was a roadmap and there was a lot more information, okay? That's all. All right, so let's at least, play with the graph for the time being. I'm going to forget about everything else about the roadmap and let's play with the graph for a short while, then we'll come back and improve the model. So here is a graph model, we saw for the roadmap. For the river network, we will use a slightly different way to make the graph. Here nodes are suppose rivers, all right? In case of road intersection, your nodes were localized. In this network, the nodes are really long things. And the relationship I might represent is falls into, which river goes into which other river, okay? So here, I said, these are all different rivers, and this two river kind of goes into that river, and these two goes into that, and so on. So this is a slightly different way to represent things, but your choice of nodes and edges are different, okay? So we can look at, for example, this Mississippi River, which is number one, and so on, and then this is probably the Missouri coming from here, and so on, okay? All right. The strength of this graph model, the reason computer scientists love it a lot is because there is a very mature mathematics about it, and it also has helped us design very, very efficient algorithms, okay? So if we can live with the approximation, then computer scientists can help you scale up very quickly, okay? And that's the beauty, and that's why we use it, okay? But as I told you, the weakness is that it only models one relationship and leaves out, it's a very coarse approximation when it comes to geographic data. And time to time, you have to think about it. But good news is that if you are doing research, you have a lot of opportunities to improve things, okay? And that's the way to view it, okay? So I said, if you want to deal with multiple relationships, you have to think again, if you're, there may be different graph models and so on. So outdoor roads, we are actually fortunate because, by mid-90s, everybody agreed on a single representation and there is a consensus. But if you come to indoor space, the graph model of indoor space, there is no consensus. So if you're going to look at indoor data, you will have same kind of problems that you have on that reference system, okay? The way nodes are defined, edges are defined may differ, and you have to be careful, and so on, okay? All right, so let's actually just show you one small thing. If I took my classical choice, road intersections as nodes and road edges as, the segments as edges, modeling turn, what happens, let's at least see. So if you wanted to model turns, you have different choices, okay? So one choice could be that, you basically use a sequence of edges, okay? So you take this particular node, but here, if I am, for example, coming from, let's say, this direction, okay, this direction, all right, so then I don't have any turns, but let's say if I come from, this direction, this is a left turn, right? And if I want to separate it, then you can actually expand this node into more edges. So you notice this node has been now broken up into a set of nodes, and then I have introduced these turns as additional edges, okay? So when I was going from this left turn, okay, this left turn, that's this edge now. And same thing, you can try to say if I am coming from other direction and going this way, then that's this edge. So by creating this, much more detailed view of this node in terms of a whole set of other nodes and edges, you could model turns. This is one way. But by doing that, as you notice, your graph size increases. Okay. So there are academic papers and people kind of talk about that. But most pragmatic solutions, what they do is to annotate the graph. So if you're looking at ESRI map and so on, they will stick to this model, but every node will have an additional table attached to it. And in that table, all possible, the turns are listed, and you can put the property there. Obviously, if you are working with that kind of a graph, it's no longer pure graph theory, because your code would have to constantly go look up the table and do things. Whereas in this model, you could stick to your pure graph theory and analyze it better. But the main message is, it only one relationship is there. If you want to model other things, life gets a little more complicated. That's all. I'm not going to say a whole lot more. Yeah, go ahead.
Could you get node part once again? That is, you break the node into four.
Right. So let's kind of think through this. So I'm trying to model all the turns here. And fortunately for us, there is one way. So there are, some turns are gone. Right? So the turns can happen is, let's go from one direction. Suppose I'm going this way. Okay. So if I'm going this way, here I can turn left or I can turn right. Okay. So those are two turn relationships. So in here you should be able to find two edges corresponding to the turn. So I'm going this way, and this is the left turn edge. You saw the left turn edge, right? And this is your right turn edge. Okay. And same way you can enumerate all of them. And for simplicity, as I said, I took out the second way here to make it simple. So all possible turns associated with this node have been listed here. And as you can see, you have 1, 2, 3, 4, 5, 6, 7, 8 or so edges. Okay? But this representation I enriched the graph. I expanded to graph. Now every turn is an edge. And if you have a restriction on that turn, like a delay or no left turn between during rush hour, those can be attached to these edges. And you can still live in the graph theory world, which computer scientists love. Okay? But the graph gets bigger. Okay? But there are other ways to do that, but now you will have to step out of graph theory. Okay? Yes, go ahead.
If we store coordinates of all the intersections and calculate the slopes, and then we can find what type of turn it is.
Wonderful, and that will be annotating the graph, right? You have gone out of the pure graph theory. Okay? So the interesting part about roadmaps is that it has both geometry and graph. Okay? But in computer science, when we study these things, when we study graph, we just study graph. We study computational geometry, we just study computational geometry. But this world, you have to mix the two. Okay? And a lot of times the opportunities will come from that. Okay? Sometimes it's better to view roadmaps as graph. Sometimes it's better to view it as geometry. Sometimes you want to interplay both. Okay? So, but in your model, it will be like annotation. Okay? And your model will do something more. So let me tell you one other thing your model will do. When I am in graph theory, the edges are atomic. Right? Edges don't have sub-edges. Is that right? Okay, but we know that these things are road segments, right? These things are road segments. They could be 50 meter long. They could have nice curved shapes. So if I have your exact geometry, I can take this edge and break it into multiple smaller edges to represent the shape. Okay, this is sometimes called dynamic segmentation. Your edge definition has been changed. All right. So there is fair amount of richness here. All I'm basically trying to tell you that once I show you a graph, don't just zoom onto the graph. It's an approximation. And remember, there is geometry. And many problems, bringing that back will help you. Okay? But you can annotate, which is often done. For every node, we would have its location, the coordinates. Okay? For every edge, we will have a line string, which will give it shape. Because otherwise, when they display the map on your Google map, you won't get the exact shape. Okay? So this classical model, yes, it does look like graph, but it does have geometry and it has other things. So that's all the point is. Okay? All right. Does that kind of address your thought? Yeah. Okay. So it looks, when I just draw a graph, remember there is more to it than graph. That's all. Don't put blinders on and say, okay, I got my graph theory. I don't need to know anything more. And that's where problem starts. Okay. You can even go to a hyper, graph model and so on, because as you know, in hyper edges, you can, have a more sophisticated thing. There are different ways to model, and this is the last one. Annotate the graph nodes with different information, with coordinates, with turns, and so on. and people have done, different kind of analysis. Commercially, this is where everybody has gone, but of course in academic paper you can see the other two. Okay, so here is just showing you, look, the graph model, even though most people use one graph model, there are many different ways to actually choose, many different ways for you to choose nodes and edges. Okay, that's all I'm basically telling you. Just so happened that in outdoor road maps, a consensus formed, and most commercial methods went this way. But there are other models, and depending on your use case, these other models may be more useful to you. Okay, just remember that. And this is not the end of the choices. You can have more of those here. All right, so this is the conceptual model part. So quick pause for a recall. Okay. All right, how many vote for turn restrictions? Okay, good. All right, so this is something to remember. All right, so they do annotation or something else to do that. So when Corman's white book puts you a challenge problem saying give me the path with least amount of turn, that's what they are teasing you about. Okay. All right, so conceptual model, that's all I wanted to say. Let's now move on to logical model. So we are now in the SQL world, and we want to write a few queries, and we assume that there is a graph here. Okay. All right. So we will go a little past 10:30 for the break. We'll try to wrap this logical part up and then take a break before we go to physical part. Okay. Okay, good. So here the focus is that, can we manipulate some of these roadmaps and graphs in SQL? So we'll talk about a few abstract data type and then show you some special statements in SQL. Okay. So in this term, main thing to remember that in SQL, now we can do some manipulation of graph, and in particular we find we have an operation to create transitive closure. So let me quickly define that for people who maybe knew it. But quick show of hand, how many of us are not familiar with transitive closure? Okay, just a few. All right. Okay, good. So we'll at least show you. Okay. So the idea is that if suppose you are given a simple graph here. Okay. So this graph has nodes 1, 2, 3, 4, 5. And these are the edges. Okay. In the transitive closure, we are essentially going to figure out all possible reachability relationships. So for example, starting with node 1, I know I can reach nodes 2 and 3 in one edge. But question is, can I reach other nodes if I were allowed to use more edges? So from 2 you can also reach 3, right? So from 1 I can reach 2 and 5. I can also reach 3. I can also reach 4. So transitive closure will show me the entire information. Okay. So in the transitive closure graph, the set of nodes does not change, but the set of edges actually go up. So if there is a path from a node to another node, then in the transitive closure there will be an edge. Okay. That's all it means. And this is the simplest kind of operation on graph before we do shortest path and so on. Okay. All right. So I said for 1, 4, we added an edge here because in the original path there, we could reach 4 from 1. That's all. So this is, in tabular form, this is your original graph, and this is the transitive closure in tabular form. That's all. Yes.
So if we take it as a procedure, sir,
Right.
First we have to see whether the nodes are connected irrespective of number of edges.
Right.
And
Right.
then we add an edge to it.
Right. Yeah. That's all. Yeah. And we'll show some algorithms in the next phase. But there are different ways to actually do that. You can write a graph algorithm or a matrix multiplication algorithm. But this is considered a building block operation. If you can work, you can implement this well on a graph, then you can use it to do many other things, including your flood modeling. And I will have an exercise on that. Okay, flood modeling is an example of this. Okay, good. Any other quick questions on this graph operation? Okay. All right. So one interesting thing to again remember, in relational algebra, the original relational algebra was not capable of representing transitive closure. Okay. So basically in order to support graphs in SQL 3 new statements were added. And we can actually, these abstract data types have not been added, but we at least can think in terms of what data types we might use. Okay. So you can, certainly we want to do some kind of a shortest path operation, and you can add data types like nodes, edge, path, and tree. But the SQL, what it has are these special statements like connect and recursive. Okay, so these are the two, and I will briefly show what they do. People who have done recursion in other languages like Python and Java and so on, you should just try to map it. It's just the syntax will be different. In SQL now you can do it. It's the same idea, but just the syntax will change. Okay. Okay. All right. So a small, quick review for people who are new to transitive closure. Okay. Okay. How many are voting for A, for example? No one, because 1 we can reach. 5. B. Okay. No votes. You can reach 4. C. Okay, a lot of hands up. There is no way to go from 2 to 3 because edges are directed, right? Okay, good. All right, so let's look at the connect statement, which can work with directed graph and do that for you. Okay, so at least SQL knowledge we are extending. All right. So in case of connect statement, we only work with sort of a directed graph and more like a and so the input is you give the edges of this directed acyclic graph. So here, for example, is our river network, where you have, let's say, this Mississippi River, and all these other rivers fall into Mississippi, including Missouri, and these ones fall into Missouri, and so on. And the output will be a transitive closure. Okay, so you can essentially go from from this node all the way to all the nodes reachable. And you can also give a start node. So a start node could be, any node, Missouri or Mississippi or Platte and so on. And when you do that, and you can give travel direction, and then it can give you either all the predecessors of Missouri or the successors. Okay, so these are the predecessors, means these nodes, from there I can reach Missouri. All these rivers ultimately contribute water to Missouri. But you can also reverse the direction and ask for successors of that node. Okay, so I can ask if Missouri has a water quality issue, which other rivers are going to be affected. Okay, things like that. Okay. All right. So I can also represent the same thing in a tabular format. So this set of edges, this is how it will be represented in SQL. This is the table name and source and destination. So for each edge here, P1 to Platte, that's the first edge, this is the second edge, and so on. So in a tabular view, because databases in SQL, everything is a table. Okay, even graphs are viewed as an edge table. Okay, all right. So here is a quick first syntax and of this connect by. So let's see what is familiar and what is new. Okay, we did see select and from yesterday, right? We all remember that. So from clause is where tables are named. In this case, this edge table is listed here. Okay. Select clause, we are basically taking a set of, subset of columns that we want in the result. Okay. So we basically want in the result only one column at the end out of this table. Okay. But then these two are new, right? This connect by and start with are new clauses that were added. And this is supported in Oracle, for example. So this is sort of what it does. It starts, so first it tells you the direction, and this keyword prior kind of tells us, which way we are going. Okay. So this prior could be placed before the first argument or the second argument, and I will show you the other one as well. And that tells us the direction, whether we are going along the edge or we are going in the backward direction. Okay. And then it also tells you the start node. So here the start node is Missouri. And in this table, you will see, there are some instances of Missouri over here, some instances over here. Okay. So let's try to understand what it is doing. Is it giving me predecessors or is it giving me successor? That's your only choice to figure out. Okay. All right. So to understand its result, this is how we work. Okay. We first say, okay, in the sources is a set of nodes. You initialize it with Missouri. Okay. We initialize it with Missouri, where Missouri is in the destination column. So you look at this column, and there are two instances of Missouri, and so these two rows are where we have to start. Okay. So we start with over here, and then so destination is Missouri, and then you look for the sources which are associated with that destination. So out of this, so these are the initial two sources. Okay. We are kind of going backward, the initial sources. And then you have to recurse. So if any of these sources show up as destination, then you have to take their sources. So that's basically what is happening. Okay. So if you want to sort of look at the execution trace, we started with destination equal to Missouri. All right, and then the direction of travel is backwards. So from we went back here, so from this you will go pick up Platte and Yellowstone. From Platte you will pick up P2 and P1. From Yellowstone you'll pick up Y2, and that will be your end result. Okay. The alternative is we can put this keyword on the other side, okay, and then you can go along the edges. Okay, so that's all there is. Okay. So if you know transitive closure conceptually, all this tells you is there is a syntax in SQL to compute it. That's about all. Okay. Okay. Any quick questions, issues on this one? So if you think about recursion, in recursion always there is a base case and a recursive case. So this is your base case. Okay, this is your base case, saying this is where computation will sort of start. And then you have to carry through. It's sort of like a directed acyclic graph, so you will basically go through and traverse the graph level by level. Okay. We will spend a little bit more time on the next statement, recursive, which is part of SQL 3 standard, and it's supported by many more vendors. Okay. But this just showed you one thing. Okay. All right. Okay. So essentially, I said, no, from here you came to all the contributors. So from here we went to Platte Yellowstone, from Platte we went to this, and from Yellowstone we went to that, and that's where the recursion ends, because these things don't show up on the other side. Okay. All right. And I said, you can go the flip side. If you put this prior word on the other side, then you are going in the other direction. Okay. So in this case, I also notice that we will start differently. We'll start from source Missouri. So this time now we are going this way. It comes down here. Fortunately for us, Mississippi never shows up as a source. Okay, it goes into Gulf of Mexico. So this one ends very quickly. Okay. But if you had started with another river, you might have gone further. Okay. All right. So this was supported by Oracle earlier, not just for GIS, but for many other directed acyclic graphs. So if you are in, for example, a manufacturing, sometimes you have an ingredient hierarchy. In order to make a recipe, you need certain ingredient. In order to make that, you have something else. So you create a tree, and this was used to traverse that kind of a tree. And you can use it for this as well. All right, so if we are comfortable with this, let me show you the other statement, recursive, which is much more common. So I'm going to skip this one for now. But just, okay. All right. So let's look at something which is a little bit more general, and that you can find in many brand names. It was SQL 3 compliant, which came in 2003. You are going to find this statement, whereas this is a little bit less widely available, but Oracle would have it. Okay. So let's look at recursive and how that is used. So, all right. So in case of recursive, again, your input is an edge table, okay, which has source and destination, a directed graph, and you can traverse the edge in either direction. All right. And this case, your recursion structure would be very like any other recursive function. You will have a base case to initialize the result, and you are going to have a recursive case to grow the result. Okay. So with this, let me quickly show, and you can add more things. And again, you can pick up very simple things like predecessors, successors, and so on. So here is the syntax. All right. So in here again, some things are familiar to us. For example, you notice the select statement inside this red box. All of these clauses we saw yesterday, right? Select, from, and where. So from, we are giving 2 tables here, right? And select, we are picking 2 columns, and where we have a condition, okay, joint condition. This is another select statement, select and from, 1 table in the from and 2 columns, okay? So things inside the blue box and the red box we saw yesterday, which, right, we are all comfortable. So let's look at how recursive works. So with recursive, you are defining a new table. In this case, the name of the table is X, and this table has 2 columns, source and destination. Okay. So this table is initialized. Okay, it's first initialized in this base case. So here is this initialization, and we are assuming table R already exists. And this table R is that little graph that I was showing you before with 5 edges. So we base case initialize this table X as a copy of R. So that's your original edges. Okay. And once we have done that, then in the recursive case, we are going to add new edges. And these are added if in the current table, if I have an edge, right, if I have an edge whose destination matches the source of another edge in my result currently, right, so then I will add this new parts. So we can maybe, I'll draw a diagram if you like, and you can see transitive closure happening here. Okay, just the syntax is different. So R is an edge which is from some source destination, right? This is one edge, and then X may have another edge where X dot destination matches, sorry, R dot destination matches X dot source. So let's actually maybe write it this way. Suppose you have edge 1 to 2 here, and you have edge 2 to 3 here, then this will give me a new edge which will pick up source of R, right, 1 to 3. So then you add, does everyone see that? This is your transitive closure, right? So if I had, is another way to think about it. So if this edge was in R and this edge was in X, then I am going to add this new edge 1, 2, 3 in X. And that's the basic step of transitive closure. That's all. So just the syntax is different, right? So, but we'll do execution trace just to kind of show that. But everyone comfortable with the new syntax? All right. So suppose this is the graph. Okay, this is our simple graph with about 5 edges, and in this case, this is the result we want to get to. So let's try to execution trace how this one will get you here. Okay. So you initialize by copying this original edges into your result, right? So I got 5 edges. Everyone comfortable this one? Okay. So now I have little bit of X and little bit of R, and then recursive clause will come. So recursive clause is basically saying that if I find a situation, like notice this, there is an edge in R which is 1 to 2, and there is 2 to 3 here. So these two, if I look at this clause, then so R dot destination is same as X dot source, then I am going to add R dot source and X dot destination, right? So this is inferred from these two, and that gets added. Okay, everyone with me? And then you can repeat it. Okay, same way you have 2 to 3 here, and we have 3 to 4 here, so we add 2 to 4. Okay, and so on, and you will continue. So just need a little bit new syntax, but now SQL has transitive closure. That's all the messages. Okay, quick, any questions, issues on this? Okay. All right, so let's pause here a quick minute and all right, okay. So how many vote for A? Okay, some, all right. B, U, C, all right, and how about the last one? Okay, a lot more hand, right? So this is just a quick summary of recursive. So all of the above is what I was hoping. Okay, good. So I think this may be a good place to pause. And when we come back, we'll be in the heart of computer science. But beginning will be simple. We'll start with depth first search, breadth first search, Dijkstra, A star. Those a lot of us know, and then spend some time with hierarchical routing algorithm, which will be hopefully new. Okay. So how long should we break now? Yeah. This is the 20 minutes, okay, and then we'll come back and do that. Okay. Sure. Okay. One announcement.
I think from our chapters at Jawaharlal Nehru University at the school, we invite Professor Shekhar for a talk tomorrow at the school. There will be 2 talks by him. We'll soon let you know about the